Per, you have the floor.
Well, thank you so much. I hope everybody can hear me clearly.
Yes.
It's a pleasure to be able to speak to everybody and to talk a bit about the topic of nuclear energy. Let me start up some slides first, and then dive on in. So I am going to be trying to speak pretty broadly about a range of different technologies and also focus in on some of the things that we've been working on and give some background. And before I start, the Kairos Power is a startup company that is mission driven. And so in meetings, it's conventional to always start by reminding ourselves about the mission statement of the company. And I think actually this is a mission that all of us who worry about questions about clean energy share. But in case of Kairos Power, the mission is to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment. So today, I'm going to try to cover three broad areas. The first is to present a bigger picture about nuclear energy and where it fits into the overall set of questions we need to answer for clean energy. The things I'll mention are it's a subset of some of the major issues that people talk about and think about for nuclear power, including nuclear waste, sustainability, that is, in what sense can you consider nuclear fission and nuclear fusion to be sustainable energy sources? And then finally, is it feasible to achieve dramatic reductions in cost and therefore have affordable and dispatchable clean energy from nuclear fission and fusion? So the next thing I'll cover is strategy for innovation in advanced nuclear. And there's a set of topics that I'll go through, including passive safety, the role of smaller reactors, advanced reactors that use alternative coolants, and then also whether there's models from other industries that may be relevant in thinking about innovation. And then finally, I'm going to cover a bit of some of the specific work that's on way at Kairos Power, which is a subset of a wide range of different efforts that are underway today in the field of nuclear power. So let's go ahead and start with this big picture. To begin with, I do think it's important for us to place nuclear waste into context. And there's a variety of different ways that one can do this. One of the ones that I think is useful is just to look at the quantities that are involved. And so in the world this last year, nuclear power provided nominally 10% of global electricity production. And that's important because it shows that nuclear power has been demonstrated to be a technology that can be scaled to power outputs which are relevant to grid scale and global scale electricity generation. And it did it with remarkably low carbon emissions, of course, because the fission process doesn't emit in carbon dioxide. The total amount of spent fuel that was generated worldwide to produce 10% of the world's electricity was about 6,600 tons, which if you were to, and this is highly hypothetical, of course, but if you were to place it on the football field at Cal Memorial Stadium, you would find that it covers an area, it would create a layer about 1.3 meters deep. Now, the use of this nuclear power offset the need to mine and combust approximately 1 billion tons of coal. And to place the relative quantities and volumes into perspective, I've shown the hypothetical pile of coal that you would get if you were to try to pile up 1 billion tons, and it would be nominally 230 kilometers tall, and you'd have to back up a bit and to really get a good perspective for the volume difference in terms of the material. So thinking about this, there's a couple of really important observations. The first is that with this spent fuel, of course, we do not have a societal consensus today as to whether that spent fuel is actually a waste or whether it is a potential future resource. And today, with today's technology, you classify it as a waste because the difficulty and cost to recover anything useful from it exceeds the value of what you can recover. but that's with today's technologies. And so the societal disagreements about whether to proceed with the geologic disposal of this material are substantial. And there is a strong scientific technical consensus that geologic disposal can provide safe long-term isolation. That is deep geologic disposal. Also, just from the perspective of effort, mining 1 billion tons of coal from its previous safe long-term geologic sequestration is clearly dramatically more challenging than placing this tiny quantity of material into deep geologic isolation, should that be what we end up doing with it in the future. So I do like to quote Michael Schellenberger: nuclear power's waste products aren't a mark against the technology, they are its key selling point. And I philosophically agree with that. Now, there's the next question about sustainability. And today's reactors consume dominantly the uranium-235 and small amounts of uranium-238 that is in natural uranium that is mined around the world. And there are ways that you can increase the fraction of the uranium that can be fissioned up to actually quite large quantities. Likewise, there are alternative fuels such as thorium and fusion fuels. The important point is that even though we consume very small fractions of the actual potential energy content in mined uranium, the costs are very, very low. And if you sum together all the costs of nuclear fuel and convert it into a unit that can be directly compared to other forms of energy, in particular, let's say natural gas, the cost of fuel today for nuclear power plants is about 40 cents per million BTUs, which is roughly an order of magnitude lower than what we would consider to be inexpensive natural gas. The potential that these costs are going to increase in the long term, I think, are very small, because of all of the things that can happen in order to improve efficiency of the use and to increase the production of this resource. So the long-term availability of fuel for nuclear energy, I don't think anybody believes would end up concluding would be a constraint, particularly when you look at the technical feasibility of extracting uranium from seawater. So this means that in the sense of being capable of providing energy over very long timescales, you can consider nuclear fission to be a sustainable energy source. Now, the final question is all of the other stuff that you need in order to build and to operate various types of infrastructure, including power plants. And considering the life cycle impacts is important. It's also quite interesting to look at the potential for cost reduction. And so I apologize, this table is a bit of an eye chart, but what it does is it summarizes the different types of materials that are used to construct different types of technologies. And so this is from actually one of the major life cycle studies for existing nuclear power plants. And these are the quantities of concrete, steel, copper, et cetera, that are needed per kilowatt. And what I've done here is I've multiplied them by commodity prices. These today are a bit low because, of course, we're in a period of high inflation, but the relative cost in comparison remains largely correct. And you can total them together and conclude that there's about $34, $37 per kilowatt of investment that is required to purchase the raw materials that are needed to build nuclear power plants. And when wind turbines actually are far more effective in terms of the cost to convert the material into the infrastructure. And so you can see for wind turbines, it's about $200 per kilowatt. And then you can do the same comparison for automobiles. And a Chevy Malibu, of course, is a fairly sophisticated technology and such. The thing that's quite remarkable is the fact that nuclear power today, less than 1% of the purchase costs are actually paying for the materials that are being converted. And this is nominally an order of magnitude lower than the ratios that you would see with most types of conventional construction manufacturing. There's no physics that require nuclear power plant manufacturing construction to be this expensive. And the big question is, are there ways using advanced reactor technologies that we could reduce this ratio significantly? Because if you could do that, you could see the potential for very dramatic reductions in the cost for construction, manufacturing construction of nuclear power plants, combining that with the very inexpensive fuel and with the potential to achieve much higher levels of automation and reduce the required staffing levels from what the Gen 2 plants require, which is quite enormous because they're 1960s designs. There is a very credible future where fission energy is very inexpensive and abundant, and therefore can play a major role in helping us to decarbonize world electricity supply. So with that, this raises, of course, the question about how to innovate. And so I'm going to touch on a few different dimensions of this question because it's probably the most important question that people who are working in this field today need to think about and are thinking about solving. So I'll touch on a few things. Let me begin with what I would call an emerging U.S. innovation path for new nuclear technologies. And the key element, particularly for fission systems, is the use of technologies that enable what's called passive safety. And this addresses the fundamental issue with the early generation 2 reactors, which is that in those reactors, the major safety function of removing heat after a reactor is shut down. Because while you can design reactors to intrinsically reduce the rate of the fission reaction as they heat up, which that negative temperature feedback is an absolutely essential element of reactor design. And you can design them with passive systems that can stop the fission reaction with very high reliability. Those things have been done in reactors over history, except some of the Russian reactor technologies, such as the RBMKs, a consequence of that was the Chernobyl accident. So when reactors are designed that way, then the principal safety issue is the fact that even after the fission process is stopped, there will still be decay, radioactive decay of fission products, which will release additional energy. And early on, it's a couple of % of the original fission power because you have short-lived fission products. Of course, those are decaying away more rapidly. And by the time you're out at about 24 hours, you're down at around 0.5% to 1% of your original operating power. This heat must be removed reliably. In the existing plants, most of them, the technology to do that involved active systems with redundant pumps and power supplies and other things of that nature that required electrical power to function. And one of the key things that happened in the Fukushima accident was the loss of all sources of off-site and on-site electrical power. And that led to severe damage to reactor cores in 3 of those reactors. So the transition to passive safety actually has been has been accomplished. I'm not aware of any current designs being offered by any vendor in the world that doesn't have capability to shut down and remove decay heat using purely gravity-driven processes without the need for external sources of power. And moreover, where that safety function of decay heat removal is actuated by removing external sources of power rather than having to provide external sources of power. So those changes dramatically simplify the safety design and also improve the reliability of the safety systems for advanced reactors. And we should expect all future reactors to do this because it also makes it much easier to implement physical security for plants. If your major goal as a security force is to disconnect power from the safety systems, as opposed to assure that you can continue to maintain power under conditions where a plant is, where something is happening to a plant, that's a very important transition. The next thing is small modular reactors. It's important to emphasize that in nuclear power systems, there are economies of scale. There are reasons to build larger reactors. However, if you want to innovate, it is far easier to do it, at least initially, with smaller reactors. And this is one of the reasons that the development of strategies to do multi-unit SMR installations, where you get one reactor design that's relatively small to work well, and then you install multiple copies of that, is a great idea. And it mirrors what SpaceX did, because if you look at SpaceX, they developed a really small rocket called the Falcon 1 with a small compact rocket engine. Their next major product was the Falcon 9, which used 9 of these same engines. And they also proceeded to uprate the power output from those engines. The initial engines were 320 kilonewtons. Today, that's packaged in that same volume. The Merlin engine puts out over 800 kilonewtons. And so there's a variety of things in terms of SMR architectures which facilitate innovation and iterative development. And then finally, the next major question is, how do we transition, and when do we transition away from using water as the primary dominant coolant for commercial power plants? Water has worked relatively well. It has a few serious deficiencies as well in terms of the behavior of water-cooled reactors and accidents, which has issues around the way the fuel is damaged and the way fission products are mobilized that are not the same when you transition to the alternate coolants, which are liquid metals, gases, and molten salts. Each of these alternate advanced reactor coolants has a set of attributes that can make them desirable, and also a set of things that can be issues with them. I will focus on molten salt as one of the examples, but there's many applications for reactors, and there are appropriate applications for each of these different coolants and different types of advanced reactors. And of course, moving towards improvements in safety and efficiency as well. So as I'd mentioned, there's a large amount of work, many companies today who are working, and this includes incumbent industry, your GEs, your Westinghouses, your Framatones. This also includes a remarkably large number of startups, just because it's the mentality in the United States to do startup companies. The majority of startup companies in the fission and fusion arena are US based, and that includes one of the ones that I and Mike Laufer and Ed Blandford co-founded, which is Kairos Power. So this creates a remarkable environment. There's also a remarkable environment in terms of new non-governmental organizations, such as Third Way, that have been active over this last decade, remarkably active in thinking through policy questions around what would it take to enable nuclear power to play a more substantive role. And they've done huge numbers of very thoughtful studies. They've been advocates in policy space, and they've also been successful in gradually shifting the conventional wisdom within the environmental community that nuclear power has too many problems that cannot realistically be solved, to be one of actual optimism that done correctly with appropriate policy frameworks, nuclear power could play a major role in enabling us to decarbonize world energy supplies. So the other thing that I think is worthwhile is to look at other industries and seek examples for better practices. We've looked extensively at biotech, for example, because in the case of biotech, the Food and Drug Administration has different practices from the Nuclear Regulatory Commission in terms of how they regulate the development of medical and technologies and drugs. And if you think through it, the biotech field is one that is heavily regulated, and also where remarkable, absolutely remarkable innovation has occurred at a rapid rate. And you look at realistically, we now have ability to cure certain types of cancer. This is absolutely phenomenal. What are the characteristics and differences between the FDA and the NRC, where because we have had a dearth of innovation on the nuclear side? Another example actually is commercial space flight. And if you look at the conventional development approach that the United States used to develop launch vehicles, with the space shuttle being the best case study, and this is the conventional cost plus contracting, the sort of the conventional supply chain approach of dividing the project up into many different pieces that interface through requirements and require large numbers of vendors to hypothetically work in a completely sort of integrated way. And then finally, picking an architecture for a launch vehicle where intrinsically you had to have astronauts fly with cargo. So every single flight, and starting from this large scale, had to be perfect because the consequences of any kind of failure were the loss of human life. And so that combination of factors combined with a couple of accidents ended up causing the technology to be extraordinarily expensive. And by 2005, 2006, the United States had lost completely any market share in commercial space launch. So then you have a startup. 2002 was founded, named SpaceX. Somebody many people know the name of these days, Elon Musk, had this vision to make access to low Earth orbit much more affordable, starting by developing a small single engine rocket, and then successfully on the fourth try, launching it in 2008, building a new design with 9 of those engines, having it successfully deliver cargo to the International Space Station in 2012. By 2015, successfully re-landing and making the technology reusable, which is absolutely remarkable. Notice that these don't look the same. The one on the left, I could explain easily to a congressperson why that is a reusable spacecraft. And if the government is funding stuff, that's pretty much, it has to be that simple of a story. The one on the right, the fact that you can re-land it, is just absolutely remarkable. And there's a long story behind it, but they've achieved reusability. By 2018, therefore, over 50% of world market share for commercial space launch returned back to the United States. And of course, today working on an absolutely amazing new technology called Starship, which has the potential to achieve another factor of 10 reduction in cost. So could you do the same thing with advanced nuclear? This is a really important question. You're not constrained by the natural resource inputs. That I showed you the statistics. The question is, how do you learn from what companies like SpaceX have done and in biotech and do nuclear differently? So one of the key elements that SpaceX developed, and this is actually a chart stolen from a SpaceX presentation by from John Murator. Before he actually came to work in the advanced nuclear industry, he was at NASA and stuff, and then at SpaceX. And the big issue with the conventional nuclear development cycle is that you get stuck in a plan design loop because you've got these massive, difficult projects that have very high risk and need to be perfect. It's a space shuttle type of mentality. And you get to the point where oftentimes you get stuck in this loop and you never actually build and test stuff. And what SpaceX did was to develop a strategy of doing multiple iterative cycles to prove out how technologies would work and to retire risks much earlier in the process for the function and capability of the different systems that they had. And so you can represent that as iterative: plan, design, build, test. Learn from the test experience, plan, design, build, test, learn from it, and to do these larger loops and smaller loops rapidly so that you can rapidly improve the technology. So in the case of Kairos Power, this approach is fundamental to what the company has been doing. And so let me spend the last part of this before we get into questions, talking a bit about Kairos Power, which is one of the many startup companies that are working in this advanced fission, advanced fusion community. So Kairos is a nuclear energy engineering design company that is focused on commercialization of we call it fluoride salt-cooled high-temperature reactor. This is one of the subset of reactors that uses molten salts. I'll describe it in a moment why molten salts are interesting coolants. But the key thing about the FHR is that it transitions from the historical approach with molten salts, which was where you would dissolve uranium into the salt so that you would have a liquid fuel, to making use of high temperature solid fuel that had been developed for gas-cooled reactors. And this transition to using solid fuel carries a set of benefits, including simplifying the licensing process that I'll describe in a moment. We co-founded the company in 2016, derived from a major research program, multi-university, UC Berkeley, MIT, University of Wisconsin, University of New Mexico, and other universities that studied this technology and developed scientific technical basis for deploying it. Today, Kairos Power is staffed at 280 employees, located at multiple sites. 90% of the staff is trained in engineering. We have private funding commitments through the development demonstration of a small demonstration scale reactor. Our schedule is driven by being capable to have commercial demonstration by 2030 to enable a rapid ramp in the use of this technology subsequently. And the key point is to have cost targets that are competitive with natural gas in the US electricity market and to pursue licensing in the United States. So these are the locations of current Kairos Power facilities. We've grown rapidly. That process of growing organically is one that needs to be a part of what you're doing in parallel with solving the problems, because that ability to scale up has to translate subsequently into the scale up in the manufacturing capacity and the ability to deliver large numbers of reactors. So that question of how do you successfully grow is quite important. So I'll introduce you to the California facilities, which are located on Alameda Island, formerly Naval Air Station. So this is actually, it's a gorgeous historic aircraft hangar that has been converted and co-locates laboratory facilities with engineering and design, so that engineers are very much driven to be hardware directed and work directly with the hardware, both in scaled models as well as in full scale prototypes. Then we have the New Mexico facility. That's actually where I am today, where we call this T facility. And this is where we're building a full scale demonstration reactor, electrically heated, we call the engineering test unit. I'll show you that. We are producing the unique coolant, this molten salt, lithium beryllium salt, in the molten salt pilot plant with our partner Materion. Materion is the world's largest supplier of beryllium-based products in the world. It has 80% of the world market share. And their facility in Elmore, Ohio, actually produces beryllium fluoride as an intermediate step in the subsequent production of beryllium metal. So we're partnered with them to produce this unique salt. We have acquired and are in the process of obtaining a construction permit from the U.S. Nuclear Regulatory Commission for a demonstration reactor to be located in Oak Ridge, Tennessee, adjacent to Oak Ridge National Lab. And the majority of our licensing team is headquartered is based in Charlotte, North Carolina. There's a lot of talent there in this area, and it's also a much shorter plane trip to get up to Washington, D.C. and to visit the Nuclear Regulatory Commission. So the basics, the fundamental basis behind the technology is the combination of what we call coated particle fuel. These are poppy seed sized granules that contain kernels of high assay, low enriched uranium at the center. This fuel was developed under a DOE program, an advanced gas reactor program, over the last couple of decades. And the improvements in process control and manufacturing have resulted in this being the most reliable coated particle fuel that has ever been manufactured in the world. It was originally, the TRISO type of fuel was developed in both the United States and Germany. And today the capability to do the manufacturing is remarkably good. Furthermore, the fuel has been qualified We use it in the form of pebbles. They're ping pong ball sized. This pebble that you can see being held between two fingers contains 6 grams of high-assay low-enriched uranium in these kernels, about 16,000, and can produce thermal energy equivalent to the combustion of 4 tons of coal. And so, of course, this is an interesting thing to be able to say that you could pick up 4 tons with 2 fingers. That's actually, in a sense, true when you think about our fuel. This is the coolant. It is a molten salt, and I want to go into a little bit about thermophysical properties because that's important. And so this is a list of various different coolants which have been used and demonstrated as coolants and heat transfer fluids in various types of reactors. And of course, the majority of reactors today use pressurized water. They actually have to operate at relatively low temperature. What differentiates the molten salts is first, they have very high volumetric heat capacity. That's the product of the density times the specific heat. And you can see that the volumetric heat capacity applied is even larger than water. The implication is that moving very small volume flow rates around, you can transport enormous amounts of thermal power. The other important attribute is the very, very high boiling temperature, which means that you are always at atmospheric pressure with this coolant. And being able to operate at low pressure, ambient pressure, and not having sources of stored energy makes the safety of the reactor far easier to implement. And then the final thing is that the fluoride salts are highly chemically stable. So you don't have the stored energy, say, that you have with sodium, which is a highly reactive coolant. So this combination of attributes actually, this was the reason that molten salts were chosen back in the day when we were developing reactors for all sorts of different applications, including one that actually was crazy, but the idea that how would you develop a reactor that would go into and power an airplane? And if you think through it, the attributes of a reactor that could power an aircraft are that it has to have an enormous amount of thermal power per unit of weight, which is a really good thing. And it has to have the ability to deliver heat at a high enough temperature to drive a gas Brayton cycle. And delivering heat at high temperature is also a good thing. This is what makes molten salts interesting. So as I mentioned, major US research program validated the basic concepts and strategies around how you could design, test, and license molten salt cooled reactors using high temperature fuel. So at Kairos, we recognize that the iterative development approach, so that you build and test hardware first in scaled systems, some using simulant fluids, which is Rapid Lab. This is largely water and oil scaled testing. Salt Lab is work at small scale with the prototypical salt to study things like corrosion, volatility of the salt, chemistry. T facility is where you work at the component scale, and user facility is the future facility where we will provide training to the operators of commercial KPFHRs. And here's another representation of the major loops. So the engineering test unit, non-nuclear, Hermes reactor, nuclear, but a small demonstration. U facility, another non-nuclear full-scale iteration, and then the actual first commercial plant, and then subsequent plants. So let's introduce engineering test unit. Why do this? Well, the big issue with delivering nuclear systems on schedule, on budget, has been the challenges in manufacturing and constructing the systems and unanticipated problems that have caused substantial delays and cost escalation. By building a non-nuclear electrically heated prototype and proving that you can manufacture the equipment and get it to work, you can retire a large set of the risks. You also have to do a whole bunch of other things that are important, such as basically INC and other things. And so, let's see. Okay. So you also test out supply chain. You have opportunities to prove out your ability to design and testing and operations. So this is the function. This is December 2020, Albuquerque, right over there. Base mat slab for T facility building, adjacent to an existing building. This is 3 months later. Full-scale building, kind of looks like SpaceX, except it says Kairos Power. This is where the ETU is at this end. We have additional manufacturing capacity here. Pretty impressive to be able to accomplish all of that work in such a short period of time. So the Secretary of Energy, Jennifer Granholm, Senator Martin Heinrich visiting here in August, manufacturing of graphite. The graphite reflector structures, the capability to manufacture this kind of infrastructure is important. Here we have the primary salt pump derived from scaled water testing. So using the similitude between water and salt, because you can match Reynolds and Proud number at 40% scale in a water system, you can actually make the components out of 3D printed plastic, which is very, very convenient because you can iterate the hydraulics design, then go into 3D printing for the full scale impeller. This is the team at Barber-Nichols, which helped SpaceX develop their turbo pumps for the Falcon 9 engine, the Merlin engine. And this is the full scale prototype pump right now installed in engineering test unit in commissioning to go into hot argon testing within the next couple of weeks. So how do you move salt around? Remarkably small pipes. So this is primary hot leg, cold leg piping laid out, welded, stainless steel 316H. This is the initial prototype vessel after installation, insulation, work platform installed, and this is the process of installing graphite reflector blocks. And as I mentioned, we're going into hot commissioning in the next couple of weeks. You have to have controls, so you need to have a control room, setting up the ability to move large amounts of data around, and to do that in a seamless way using open source technologies, and also to be able to monitor and transfer that data to remote locations, such as the support room in Alameda from here at KP Southwest. This is all stuff that we're learning. Now, from perspective of the Hermes low power demonstration reactor, the strategy is to make use of historic experience from programs, especially the molten salt reactor experiment. There's a very large amount of technology overlap, as well as the technology development and commission testing that we're doing in T facility. And you'll notice there's also sort of a common architecture to the buildings and the civil structural part, leading to the first iteration on a functioning non-power reactor. It will dump heat out to the air, which is the Hermes. Operational in 2026 is the plan. We're well along in the process. We had submitted 9 or 10, probably 11 topical reports to the US NRC. 7 or 8 of them have already received final safety evaluation reports from the NRC. Those topical reports retired a whole set of licensing questions, allowing us to submit our construction permit application and have NRC accept and docket it last November. They are now well along in their initial review, and we've been answering questions related to the construction permit application, which consists of a combination of a preliminary safety analysis report, which focuses on the reactor, as well as an environmental report that focuses on the site and the site characteristics. And the NRC has committed, and we are committed to providing timely response to their questions, to completing the construction permit application review within 21 months, which means that we expect to be able to have a construction permit in place by October of 2023. If we keep on schedule, which is not, that's a challenge. So then the thing with these major hardware iterations is that you need to start the next major step at the time which allows you to learn from the previous iteration, but as soon as you possibly can. So you can see these are the major activities for the engineering test unit. We're completing construction. We're actually, I should move this forward because as of this week, we're in the initial testing phases. Also, Hermes Reactor, we're in the CPA, construction permit application review. We're in the initial design as well, leading to construction and operation, U facility, and KPS. So in summary, I think that one of the most important points is that nuclear energy has the capability to produce tremendous amounts of power from remarkably small quantities of natural resources. And so from the perspective of sustainability, one way of looking at it is that if you look at the current, if 1% of the current construction costs for nuclear power plants pay for the raw materials, and it's generally 10% for other technologies, the cost of these materials would have to increase by an order of magnitude before nuclear power would become, before it start to become important, the natural resource consumption. I think all of the ways you look at it, you can consider nuclear to be sustainable from the perspective of efficient use of resources, just as good as things which are renewable, which also consume resources and produce waste, but dramatically less than what happens when you mine and burn fossil fuels. And our primary goal is to cease the use of fossil fuels as a source of heat through combustion. That's what we need to do. So there's challenges, but there's also opportunities and innovation. To innovate, you have to change. And so Admiral Rickover is correct. You can read the quote. This is not easy stuff. It's wonderful that we have many parallel efforts underway, taking different paths to try to solve these problems. And molten salts are interesting because of their fundamental attributes. So we should expect a significant set of future advanced reactors ultimately to be molten salt based, but we'll end up seeing the best and the brightest, youngest people are coming in to work in this field because it is literally a place where a young person can come in and do things that have the potential to dramatically change the future of the world and the future of humanity. And that's the thing that gets us up in the morning also here and in all of the other startups. And so with that, I'm going to conclude this discussion and move into questions. Thank you.
Thank you, Per, for this fantastic talk. I think there's a question on the panel on asking, we have this ping pong ball sized graphite with many triso particles, and from the point of view of heat transfer, wouldn't you have the small triso particles be the best? And I think along that line, could you also comment on the decision to not use the prismatic graphite versus the pebble bed?
Those are both excellent questions. So to the first part, picking the size of a pebble is actually something that you agonize a fair amount on. The gas-cooled pebble bed reactors use spheres at about 6 centimeters in diameter and generally operate at power densities about 4 to 5 megawatts per cubic meter, because the truth is that gases are not very good heat transfer agents. You have to circulate enormous volumes. Pressure drop and circulating power are big issues. What we discovered when we looked at the liquid coolants is that the circulating power is extraordinarily low, and you can add back huge amounts of heat. So the heat transfer is also dramatically better. So the optimal size with liquid cooled reactors in terms of balancing all of these factors is somewhere between 3 and 4 centimeters. With moving to 4 centimeters means that you manufacture a smaller number of pebbles. And you couldn't go down to the kernel size because then the permeability of the bed would be too low and you wouldn't be able to pull the heat out of it. So that's the motivation. With respect to prismatic versus pebble, the graphite is less dense than the molten salt. So intrinsically, you've got positive buoyancy, positive net buoyancy. That's a challenge with fixed fuel elements if they want to float up. And you can solve those challenges. But when we're faced with it, what we realized was that having your fuel float is actually ideal if you are a pebble bed, if you're a salt-cooled reactor, because you actually remove the pebbles from the top of the core, the opposite of helium, and you inject them into the bottom of the core, and that allows you to have a pool type of configuration where the reactor vessel has no penetrations below the top. And having no penetrations then means that you have high reliability in having coolant in the vessel along with the fuel. And so and the online refueling also gives you higher fuel utilization efficiency and allows you to exchange the fuel at a rate where you can maintain reactivity, but only just barely the amount of reactivity needed to stay at the power level that you want to have.
Mm-hmm. And maybe a related issue is these pebbles need to be mechanically, I guess, wear resistant and have certain impact strengths as they probably collide into each other. And what kind of testing have you done?
Oh, loads of testing. So in our pebble development lab, we do a wide range of different tests, including compression strength. In the gas-cooled reactors, pebbles are subjected to fairly substantial loads and substantial wear because in helium, the friction coefficients are large, about 0.6, because it's essentially very dry conditions. And with the molten salts, though, there's two really important things that impact the environment for the pebbles. One of them is that FLiBe is actually an effective lubricant. We've done lots of tribology testing. And so the friction coefficients drop. That also means wear rates are lower. The other thing is that by being nearly neutrally buoyant and having a much smaller, more compact core, the contact forces between the pebbles are dramatically smaller. It's about a factor of 50 lower force. And so that, of course, that means that the friction and wear are different. A major function of the engineering test unit is to demonstrate that we can circulate pebbles and verify the wear characteristics. But we do expect that in the molten salt cooled reactors, the environment for pebbles will be much more benign and they'll see less wear. And therefore, which is all of this is a very good thing with respect to the health and performance of the fuel.
Mm-hmm. And I guess whatever the wear product, you have to clean it out of the salt. So there have to be particular removal. And could you comment on, beryllium is toxic and sort of the selection of, why not chloride, why fluoride, and why beryllium and lithium?
Yeah, this is for a thermal spectrum reactor where you use the graphite and the coolant actually to slow down reactors as opposed to fast spectrum. A quick side note, for fast spectrum molten salt systems where you run with much larger concentrations of fissile, including plutonium, the only practical salts are the chloride salts. And this is the reason why the fast spectrum development efforts, for example, at TerraPower, have gone off in that direction. On the thermal spectrum side, where there's other advantages, beryllium fluoride and lithium fluoride have very high moderating capability and the lowest parasitic neutron capture, which means that is the combination that allows you to design reactors that have negative coolant temperature and void reactivity feedback. Those are the primary attributes. Then you get to the fact that working with beryllium requires significant controls, but those controls are very similar to what we have when we work with radioactive materials. So in fact, there has been, in some strange way, a major benefit to working with beryllium. We do a lot of work with surrogates, by the way, like Blynac, which doesn't have beryllium because that's easier. But by working with beryllium-based salts early on, we've had to implement a lot of the health and safety practices and develop capabilities that will translate directly to operating the nuclear reactor systems. Once you've got radioactive materials around, the incremental hazards of also having beryllium are very modest. Beryllium is not classified as a hazardous material from the perspective of disposal, which in turn means that essentially it in some ways it forces us to prove things earlier on as a company in terms of competencies that increase the credibility that we'll be able to run reactors as well.
Mm-hmm. And one last question is since you are building out really all the pumps and all the welding and all the pipes, so you also have quite a lot of first of all kind component. Do you see, are you thinking of making all those within the company, or you do have contracting them out? What's the situation like with the domestic supply chain? And finally, like what kind of additive manufacturing, would that be of help to you?
So yeah, the situation with the supply chain in the world is not great. And working through those challenges and getting the ETU still deployed has taken an enormous amount of work. So Kairos does work with external partners, but there is a philosophy that we need to vertically integrate the manufacturing of the major components in a way that's similar to what SpaceX did, principally because separating them apart, having them produced by multiple organizations with trying to do the requirements of the interface is extraordinarily difficult. It's also extraordinarily difficult to manufacture yourself, but at least then you're responsible for and control of your own problems. The other part is that it is very helpful to have extraordinarily compact reactor. The attribute of extraordinarily high thermal power per unit of weight has the corollary that particularly down at the demonstration reactor size, it's actually a remarkably small piece of equipment, which does make it more practical to manufacture components internally because the scale of your manufacturing is much smaller than what is required for the other classes of reactors.
Great. Thank you, Per, for this fantastic talk, plenary. Really appreciate it.